So it's all set right now. So we can basically start presenting whenever it's ready. Once you're done, you have to press this one stop
Stop
broadcast,
broadcast.
and then you have to hang up the call.
Oh.
That's it.
Mhm.
Okay?
Okay. Right, thank you.
No problem. So let this be here. And this
Hello.
Hey. Set up everything early today. Huh? Set up everything early today. That's good. Here's the
Oh, thank you.
laser pointer. Yeah. Come on.
Oh.
可以啊，我在。咬不动。我以为是咬不动。You're not supposed to be biased, but not supposed to be biased. Do you come to the open office? I'm going to make it. It looks good. Yeah, I thought it was actually interesting.
I don't think it's the future kind of approach. It's too,
What are you going to do?
yeah, because it's sort of not very elegant.
Huh?
What he's doing is it's not, it's not, I think you learn something, I'm not sure enough which would use.
But that's how the people do things for the downscaling, right?
Yeah, but he's trying to upscale. Downscaling is fine, but upscaling is not.
We didn't explain why that's down, but it is interesting that you see some strong upscaling effects of this.
Yeah, but in the Benguela region, it didn't have that. It was getting worse.
Right.
Okay, which is true. I guess the conclusion is that going to high resolution is not changing things. Unless you change the surface length. That seems to be.
Can you, Shiva, explain the process of setting it up even a little more in detail?
Yeah, I only figured it out as
So I was totally confused about how we set the boundary condition, and the same question: how does the internal small high resolution things affect the process from things outside?
Yeah, but that's for most people that would be too technical.
Oh, but it's easier.
I mean, this is something new. I mean, not many people do that. So you just need to show like a schematic kind of thing.
Yeah, relaxing the
What goes where and how does it
It's
affect.
restoring. It's restoring
the pump to the ROMs.
ROMs, which is interesting.
So basically, if it's cooling, you get the cooling.
Right.
But you're going to kill the energy conservation. You have a source.
I wasn't there.
Unless the total integrated energy is the same.
But there's no guarantee.
There's no guarantee. Okay.
Okay. Hey, good afternoon, everyone. It's finally my turn to introduce my work. And my topic is study on the Southeast Atlantic SST bias problem. So I think most of you are kind of familiar with my work, but for those of you who don't know my works, I will give a brief introduction. So the bias we're talking about is mainly the SST bias in the model. So and both ocean only and ocean and atmosphere coupled models. And here is an example for the bias that we're talking about. These are for CCSM 4 and 3 SST. So this is the region that we're concerning about. In the Southeast Atlantic, along the Benguela coast of Africa. And there is very prominent SST warm bias in the model. And this figure is just to show an example of how the bias looks like. And our goal is first, of course, is to reduce this warm bias in the model. And second one is, I think is even more important, is to understand the mechanism of the bias formation and the oceanic contribution to the bias. So
It looks like the situation's bad in the Southeast Pacific also.
yeah, this kind of bias is like everywhere. It's both in the Southeast Pacific and in the Southeast Atlantic. But they are, what we think is that they are caused by different mechanisms. So just for our topic, we mainly consider this Southeast Atlantic region.
One comment. It's mainly the upwelling regions. That's where you see the hydrothermal flows in both the sides. And if you include the whole, like global domain, you also see the same pattern in the California current system on the northern side.
Yeah, it's.
And then, of course, you also have the bias along the western boundary currents. That's for different reasons. The Gulf Stream, you can see that just cutting off the polar dirt is actually really prominent too.
So it's a boundary.
It's a really boundary.
Yeah, boundary. Yeah.
It's actually quite interesting. A lot of the bias occur in the
Well, the ocean is forcing that.
What do you say?
The ocean is forcing that.
For the eastern boundary bias is mainly in the upwelling regions. Okay, and I can introduce some previous works. So the first one is by Zhao Xu, and it is a pretty like classic paper for our works. And this is he also used ROMs, and this is the average from 2004 to 2007. So we can see that along the coast, the warm bias is pretty much reduced, and we even get like a cold bias here. But 1 or 2 degrees away from the coast, we still have a pretty huge warm bias.
What are those three things?
Sorry?
What are those figures?
These figures, so these are regional models. So which means a smaller domain and middle domain and larger domain. So he did 3 sets of models, and they are in like 3 different domains, from small one to large one, and he just show the differences here.
This is the runs, ocean only runs, so it's not a coupled run.
Yeah, this is not coupled.
So this is an average over the entire period?
Over
3
over
years
this
period.
entire period.
So this is maybe in some seasons it's worse than others?
It is, yeah, it is possible in some season that is worse, but
So all the picture he shows in the previous slides is also long-term mean. So it's did not include the seasonal side.
okay, anyway, this is his previous work, and the bottom panel I showed here is what I did last semester. I just took like 2 snapshots. Is and monthly average in 2006 in November, and monthly average for December in 2006. And I'll talk about the model setting about this run a little later. And we just see that when the model goes to November and December, this kind of warm bias here is fully formed. Okay, so for my previous run, we did not reduce the warm bias here very much. Okay, this is just an introduction of my previous work. So here I'll talk about my new runs, and here we basically have 4 new runs, and these 2 3-kilometer runs are made by me, and the 9-kilometer runs are made by Jason. Thank you, Jason. And so this one is my old 3-kilometer run, and the time is different from these ones. It's from 2006 in May 1st to 2006 December 31, and the initial condition is from CFSR. Boundary condition is also from CFSR, and we didn't do nudging in the old model. For the odd atmosphere forcing is core 2, and these are my new 3-kilometer runs. And the first one is forced by core 2. And the time is in 2005. It's from January 1st to December 26th. So for these models, we output a 10-day average for our study. So they're like 36 output files. So it's not the whole year. It's not from January 1st to December 31. But it's pretty much covers the whole year, so that is fine. And the initial condition is a 9-kilometer spin-up run, which is done by Jason. And okay, here I want to explain the 9-kilometer spin-up run. Jason did this spin-up run for, if I remember right, it's for 20 years, from 1984 or 5.
1987.
Oh, 1987. Okay, thanks. So it's long enough to spin up these runs. Okay.
Now, what was, say, I don't know what
This
two is, but what is the forcing? So wind,
is wind. It's basically atmospheric forcing.
so it's just wind.
No, not just wind. It's wind and like shortwave and long wave radiations and all the atmospheric forcing.
So core two, the history of core two is that, for the ocean community, we don't do, people always using their favorite forcing field was the ocean. Atmospheric community always that everybody use the same SST. But there's a very simple to specify atmospheric forcing field. Oceanography is really hard. Everybody have their own favorite forcing field. So it's really difficult to make comparisons between ocean volume. So 6 years ago, people at NCAR and GFDL decide we should put something common to all the ocean, global ocean model should be using the same forcing, so we can do it comparison. So they come up this project that stands for, what does it stand for? Something community ocean, coordinated ocean, yeah.
Coordinated ocean and submersible.
Right, core. And so that's become standardized forcing for all the major ocean modeling group. So everybody is supposed to be using the standard forcing. Then once you get the data, you can actually compare because they come from the same source of forcing.
But it's for a closed period or an ongoing period?
It's for a period, they continuously update the forcing because the reanalysis continuously to update, right? So I think it was from
1948 to 2009, right now.
Initially 40 years.
like 60 years. And
Until current.
So
yeah,
Yeah, it ends in 2009 right now.
So it's not,
extended a little further than.
it's not updated on a continuous basis. They update it in versions, like the first version it was till 2007 or something. This is the second version,
Yeah,
it goes till 2009. So I
But they
don't.
continue to update it. Right now, it's just they couldn't get a shortwave radiation from NASA or something like that. So whenever they have the data available, they update. And the winds up, the forcing field, the forcing field are largely based on NCEP reanalysis. And plus some correction they apply. Bill Large and Steve Younger did some correction, making sure the heat flux average equal to 0 or something like that, energetically consistent.
So there are some known issues about the ends of reanalysis, being some. So any known issues they will take care of. That's how it's being done.
Is it like how many degree resolution is this?
Two
I
and
think
a
it's
half degrees.
That's important.
pretty-
It's 2.5
Very
years.
low resolution.
Resolution.
But it is 6-hour data set. So every 6 hours there's a field.
So it doesn't have any of your eddies.
There's no ADC. No ADC.
The thing was saying, we may or may not be good at it, that it is in reference force.
Right, that could be other issues actually.
It's a different run, you know, the same area.
The eddy not necessarily in the same place as in the forcing field. So
Okay.
So, when you're using that, the ocean tries to change. So it's like a relaxation to this, or the ocean wants to put heat in a region where this data says there should be cooling. What happens? How's it? Do you force certain variables to assume the values here, or do you relax variables to these values?
Well, I think it's force the parameters.
I think you have both.
It's an indirect relaxation. Usually they have a compute the sensible leak flux using the surface air temperature and the SST. Correct me if I'm wrong.
Right.
The surface air temperature comes from the core, I think.
Correct.
The SST is allowed to evolve, but that is, you can write it as a
Restrained
relaxation.
by, yeah,
So thermally, you do relax
sort of indirect.
to the specified air temperature, but dynamically you do force because you don't have any constraint on the momentum equation.
There are other fluxes too, shortly.
Right.
But those are unconstrained, they're just fluxes. But this particular kind,
And the wind stress is forced.
Force.
Yeah.
that's normal.
That's coming from, and there's no, like last time we did, there's no dependence of the stress on the ocean current itself in those runs. The stress is computed strictly offline, and we don't do the correction anymore.
Thing is, the SST cannot be too far away from the
Right.
surface air.
So thermally is definitely constrained by the air temperature.
Because the fluxes will push it back.
So to some extent, we're actually cheating. I mean, you really shouldn't look the surface temperature because it's.
That's the thing that's most constrained. SST is most constrained.
Right.
But that's what they look at.
Right. Well, the problem is that if the model have biases, then which means the model is really, the forcing field is really wrong, and the model is really wrong, right?
No, what's wrong with all this? Forget this term is actually relaxation. It's not
Right.
written like a relaxation. It's like a force. But it actually is a relaxation. You can compute the time scale.
It's about 30 days, actually. It's more than, it's less, it's probably more than 10 days,
Yeah,
2
something
weeks.
like
Yeah,
that. It's pretty strong.
pretty strong.
Okay, so these 4 neurons are all start from the 9-kilometer spin-up run. And the spin-up run is actually initialized by CFSR. So basically all 4 runs are from CFSR. Okay, so this core 2 forcing run, comparing with my old runs, so the main difference, of course, first of all, the time is different here. But the main difference is that, so first, the initial condition is different. This comes from CFSR, and the neuron is from 9-kilometer spin-up. So the field is already have a very good spin-up. So, and in the old run, we didn't do nudging, and for the neurons, we do nudging using the CFSR data. And comparing with these 2, the major difference is that the forcing is different. For this one, the atmospheric forcing, we use 9-kilometer WRF stimulation results. So the forcing is from WRF. Actually, it's a model results that we're using for this particular model. And for these 9-kilometer runs, the difference is only the resolution. And here is 9-kilometer using core 2, and we didn't change anything else. And for these 2 are the same. We just changed the resolution. We didn't change forcing or anything else. So let's move on to the results and discussions. So here I did a comparison between all the 4 neurons for the SST field. So on the top panel, these 2 are the 3-kilometer, and the bottom panel is the 9-kilometer runs. And the left side is core 2 forcing, and right side is WRF forcing. And comparing between different resolutions, we actually see that the SST features are not very different, changing from 9-kilometer to 3-kilometer. Only that we noticed that along the equator, the cold tongue here in the 3-kilometer is relatively have a larger area than the 9-kilometer.
I mean, how can you tell when you plot things like this? I don't see it. I mean, there's no way you can tell. You need to show the difference map, right? I mean, there's no way you can tell. You can quantify whether there's any differences here. We only have 1 contours. If you plot another contour, do you know the other contour is different? You can't show things like this.
Yeah, that's.
So your conclusion from the way you plotted it is there's not much difference. Is that what you're saying?
Between different resolutions, there are not very much
Which
differences.
is probably true, but it's,
Yeah.
you can't show things like that and then ask people to believe there's not much of difference.
Do you think the large differences change core to the more?
Changing core two from Wolf, I think the differences is.
Well, you can't tell at all.
You can't tell. I mean, without the difference
It's
map.
mainly from the cow scheme. Actually, the
Yeah.
possibly, you should see some big changes, but for this cow scheme.
There are changes, yeah, but it's.
Right.
Yeah, it's very difficult to.
When these are days you wish they didn't have color this contour.
Right. I think even the contour is.
Really, the many times I wish that people didn't put color. Life's support.
But the point is that next time when you show, if you want to illustrate the difference, don't make a map like this. You have to take the difference between the two fields.
Yeah.
And then we can really see how much, you can show one field and then can show the difference of two exponents.
Yeah. Okay. Yeah, that makes sense. Right. Just to show already this similar kind of thing. Just for this one, I did a meridional temperature gradient for all the 4 rounds, and also I didn't do like a difference map. So, but roughly there's not very much difference between different resolutions.
See, just to repeat what other people are saying, you spend a lot of computer time grinding stuff out. You want to see a difference rather than say there's no difference.
A difference, but
So then you have to work at it.
yeah.
Do a subtraction problem or something.
People want non-null results, they don't want null results. It's null hypothesis is no difference.
Yeah.
I mean, there's a reason also, why would you expect that difference to be small for the C-SIP temperature field, right? Just like what we said. Because both models are restored to the same SST field. But you actually see some difference. I mean, if you look at the gradient,
Yeah,
you certainly
Yeah, there
see
are differences.
certainly a smaller structure appearing in high resolution than the low resolution.
Why the meridional gradient, why not the zonal gradient? Because that's going to be bigger boundary, right? Top level.
Well, because here there's a front zone here.
In front.
Yeah, there's a front, so the front is what we consider most for the gradient here. So
So where is the front?
the front is at 16 degrees south. So from the north there's a Angola current, and from the south there's a Angola current. So they meet at approximately 16 degrees south, and they just flow westward. At that point.
Maximum in the meridional gradient. At the front.
Yeah, the
So
maximum. of the-
where is it? I don't see it.
Well, it's 16.
No.
You told me.
Not 16.
Now I see it.
You see it in the Wharf case, not in the.
It's now very obvious, but for the two cases,
That's the
yeah.
point. Yeah.
You also see the other one, right? The negative.
Right.
The negatives here.
Yeah, 21 south of that.
Well, I think it was upwelling region. So across the line, there's a very low temperature here, and I did a meridional gradient. So here, the temperature at the south is
Now,
Warmer
temperature gradient is a vector. How do we get?
No, it's
It's a
meridional.
meridian.
Meridional.
Just
a meridianal.
It's probably more useful to plot the photo gradient and take the amplitude or something. I mean, I think in the Wolf simulation, in Wolf case, I mean, you do see some differences between, more obvious difference between the three.
So is it because you're, again, your forcing is high resolution?
Forcing is low resolution.
even the wharf.
The wharf forcing.
It's all forced by 2-degree wind products, yeah.
But wharf.
Wharf is
Wolf
the
run
wharf
is
model
higher.
is
Yeah,
9
sorry.
kilometer.
So
Yeah,
Wolf run
that's
is
higher
9 kilometers,
resolution.
it's a 9-kilometer problem.
Wharf is like
So the huge difference.
Yes.
2.5 degrees.
That's right.
9 kilometers is
Yeah.
huge. That's 250 kilometers.
Right. It is huge.
30 times. So the seminar on Monday, the guy, he moved it by like 1 grid point to win and he got.
Yeah. Yeah. Because the gradient, the wind shear is so strong, drop off so quickly in the model. So it turns out that what is driving this southward current is actually the wind stress curl. So
one grid point.
one grid point generating a huge amount of shear.
I mean,
You know,
spectral
wind
model,
stress.
you're not even supposed to look at one.
Well, that's the thing. That's the thing.
Scary.
It is very scary for this problem.
Especially when you think that, when you look at the level of group points, right? Dissipation.
I know.
The artificial dissipation.
Right.
Okay, here I did several hot water diagrams for the Meridiano SST gradient along the coast. And so this is basically how the temperature gradient along the coast change with time. The x-axis is days here. So these are these are wall forcing. So we can see that in the core 2 forcings, the frontal zone we're concerned about is maybe this position. Pretty obvious seasonality here, the position of the frontal
That's
zone.
1 year, I don't see anything that obvious. Even one cycle.
Well, actually, comparing the core 2 forcing with wall forcing, we can see that the position of the frontal zone move northward and move southward again at the middle of the year. Here's
Okay,
So you're saying that.
It showed me like 3 years and each year it happened, I believe it, but it's very difficult to say in 1 year.
Yeah.
Do you have data for more than one?
well, yeah.
So 9 kilometers, we can certainly construct the seasonal cycle, but then there's also this propagation, right? What is that? It looks like the southward propagation of the temperature gradient.
Why do you see more than one gradient that's more than one? Is it the two ends of the current?
Well, because they have eddies, right?
Yeah, we have eddies here.
So eddies give you lots of gradient.
The wharf might have the same seasonal cycle, if they have so much noise, you don't see it. Unless you average it. I'm not sure, it doesn't have a seasonal cycle. It's just much noisier.
Right.
I'm pretty sure it'll have a seasonal cycle, there will be a seasonal cycle of some
I'm
kind.
sure there is, yeah.
If you average 7 years, you'd say, you do it with a 9 kilometer case.
Well, what's the bottom picture?
The bottom picture is I
CFSR,
plot from CFSR.
just for 1 year?
Yeah,
It's definitely, right?
yeah. Just because I want to compare between different resolutions. So the 3 kilometer is only in 2005, so I didn't do any extend this.
Say divided along the coast.
Yeah.
Did you a region? I mean, along did you region or just one point?
No, it's definitely not just one grid point. It's averaged for like 1 or 2 degrees, if I remember right. 1 or 2
it's
degrees.
changing longitude, so it's not fixed, right? If it's along the coast.
Yes, yeah, it's changed with, the longitude changes.
What do you know about the seasonal cycle of forcing?
I haven't looked at the forcing or the seasonal cycle.
I mean, even this thing, you do see seasonal cycle, right? In a way. I mean, you see that. I mean, you do. I mean, you can see the gradient actually it gets stronger during what is that? You're starting from January.
Oh yeah, from January.
Yeah.
So around March or so, you can see much redder color, right?
Well, yeah.
so it can-
in case.
I want to see 2 more years where it gets red. in
Yeah, no,
March.
that's the thing. How robust different axis towards the later part of the year. So that seems to be showing up in the same scene as FSR as well.
I think you'll see it, just average you'll see it. Like,
Right.
in all cases, you see it.
Right. So the question is that whether there's also a question whether the meridional gradient is the best way of defining this front.
Mhm.
If you just look a narrow zone away from the coast, whether you can see a very strong gradient right on the coast, I'm not sure. You have 2 currents converge to each other.
The strongest gradient may be away from it.
So the strongest gradient may not be along the coast, maybe actually away from the coast. And plus, in the gradient region, it's often to have instabilities, right?
Yeah.
So there probably are lots of mesoscale, which can actually tends to.
Is there an isotherm that rides with?
Yeah, that would be much better. Just look at tracking 1 isotherms, maybe.
So then you want to show the same isotherm in the model.
Right.
It could be a different isotherm.
Yeah. And the other way you can do it is you can actually calculate the convergence of the flow field or the divergence of the flow field, right?
I don't understand
I mean, the frontal zone should be the region where the 2 currents.
When you've got such noisy data, it would be, you might get the cleanest signal by looking at the variable which has the least number of convergences.
Yeah.
Yes, that's look at SST.
If you look at if you can't, if there is an isotherm that tracks the front, then you can look at that.
That would be a much better way to do it, rather than just look at the gradient and stuff. But that adds a lot of noise to it. Okay. The other minor points, the next time when you plot, it's much better to actually put a calendar.
Oh, yeah.
Days, rather than using this, nobody knows when you start, which season it is,
Yeah.
It's much better to, all those are small things, but it's better just to put a real.
Okay. And from previous ones, we although it's not very clear, I didn't show the difference maps, but the difference between different resolutions are not as large as changing the atmosphere forcing. So from now on, I just compare the 3 kilometer model results. So this one is the core 2 forcing SST field. And this one is the bias between the model results and the Reynolds SST.
What's the resolution of Reynolds SST?
Reynolds SST, I remember it was like ½ degrees, if I remember right. Yeah. This was
I think it's 1 degree. Basically, there are 2 versions of core 2, Reynolds SST, and we use the core in a core solution.
First resolution.
So actually, that's a good point. If you use the prime resolution, the core bias that you see for the lower right quad may go away. So that is basically coming from the
Interpolation.
resolution of the Reynolds slit. That was readily available, so we use that one for all our initial comparison. That is easy, I guess.
You want to get the data set as close as possible to your resolution.
Okay. The Reynolds data I get is I think it's monthly average, right? And I remember I also get the daily average Reynolds SST, and I compare my model runs with the daily SST, and it appears that the daily at Reynolds SST give a larger bias here.
These are time averages, right?
Yes.
To that, you're saying the average of the daily SST is different from the average of the monthly SST?
No, I don't think so.
Then we
You
get the
just
same answer.
You should get the same answer.
yeah, I know I should, but just curiously, it shows slightly different.
But how can you compare with daily SSC? Your output is 10-day output.
Output is 10-day, but these are all annual mean here. So
10-day access, 10-day output means is it average 10-day or just output at 10?
it's average every 10-day
Okay.
model output. Okay, so the top panel, the bias shows that we still have a warm bias here at the coast. And this one is actually the water forcing minus the Reynolds SST. And we actually get a narrow band of cold SST bias here along the coast.
In the region you just pointed to, blue region.
Yeah.
How many grid points are there in the latitudinal direction across there?
It should be like
Probably
half a
like-
degree width, right?
Yes.
So that's 50.
1.5, yeah.
So your resolution is 3 kilometers.
Yeah,
How many grid
resolution
points
speed.
within half degree?
I think it should be like 10 or 20.
Yeah.
Yeah.
So it's uniform spacing. It is uniform near the coast.
Yes,
Yeah, it's-
it is.
Yeah.
Beautiful.
Okay, there are several regions that we can notice here. First of all is the cool tongue in the tropical region. For the core 2 forcing, the cold tongue here is actually a little bit colder. The color is kind of hard to see here. But the cold tongue is have a larger region in the tropical region, and for war forcing, the region is a little smaller.
It's
and
still like less than half a degree, right?
it's less than
Yeah.
half degrees.
Less than half a degree.
Yeah, it's
right.
yeah, that is fine.
And also your color palette looks really awful.
It gives an impression that almost all of your Atlantic is
Yeah.
brightly
You need-
biased. Not just.
You should just use, I think we should use color from now on. Don't use color
Go back
anymore.
to
Just go to the plotting contour because it's easier to see, at least for the group
Numbers are really
discussion.
good. The only way is, I mean, you have to define the proper shading intervals, then you get.
No, you use color once you have the results.
Right.
Until you get to the
That's right, but before, all the group discussion from now on, just showing the contour plots. please. At least we can see what's the thing, and then we can discuss whether you want to put a color or not. Actually, it's going to be a lot cheaper if you're publishing contour too.
So Jason, you're saying that those blue regions will go away if you have to have this? So, okay, don't even focus too much on the blue. It'll
Yeah.
go away.
Yeah.
It's just good.
Which blue region?
The
south.
two lines you have there.
This one?
The one very close.
So you're
Okay.
basically getting like a half a degree or a degree
Yeah.
warm bias everywhere.
Yeah, maybe I can try to compare with the high resolution.
The other thing you can do is you can use color and contour. That way you get
Yeah.
something out.
Well, he's trying to, I mean, except he only plot one contour.
yeah,
Color is expensive, contours are cheap.
Yeah, that's right. It's really
Not-
easy
not
to
in-
plot.
not in the electronic medium.
I think there are better color schemes. This color scheme and the way you.
All right,
contour
so
it, it's right.
I've been complaining about this for a long time, and Chris made some, like comments last time, so we too will make together some comments and notes and send to all of you. So
Mhm.
Yeah.
you can have some reference.
Okay,
So the message is that it's the winds that are make the difference.
Yeah, the message is that the wind make a huge difference here.
except you don't have the wind. Do you have a plot?
Oh no, I don't have it right now.
Okay,
But as far as we know that Chris has made some wind plot, and the Wharf 9 kilometer actually has stronger wind along the coast. So it's one of the major difference between the Wharf simulation and the Core forcing.
So is it the strength of the wind, or is it the small scale features?
From what I understand, I think is the along the coast, the wind stress that have a difference here, because when we have a stronger wind stress along the coast, we have a stronger electron transport away from the coast. So which means that there's more upwelling in this region, and upwelling, this very cold water can give a cold bias here.
well,
So
you
it's-
should go to read the Justin Smalls paper. Have you read it? That's not the so-called story. You need to read that paper so you can formulate, you can understand what he's trying to say in the paper. It's not all about the winds along the coast. It's really the shape, it's actually the curl of the wind, which is very important. In other words, it's the gradient of the wind along the coast. I mean, perpendicular to the coastline. That's really important.
So that means the finer scale features are not.
That's the reason why yesterday, if you remember this week with the seminar speaker, what they did is they artificially moved the winds towards the land by 1 grid point or something, 1 degree or something. I don't remember how many.
Like
they
one
actually-
good point, yes.
And all of a sudden, you actually see the model is doing much better. It's because the winds actually drop off really fast in that model. So it is generating a very strong wind stress curl just along the coast.
So I remember in the group other meetings that there's some kind of a cliff there, right?
Right.
It's not, the topography rises very rapidly when you go from the coast to land.
Right.
So is that important, or if you had flat land? It's not,
That's, the German guy saying that's the whole point.
that
It's really the cliff, yeah. So he did an experiment where he used the low resolution orography, kept the same resolution, atmosphere model resolution, remember that? But he actually took the low resolution model orography, implemented it into the high resolution model. And then all the bias came back.
so you took the waterfront, but with the low resolution.
That's right. So what we need to do is actually doing the same experiment. I mean, we can verify that's the case
You had
here.
much higher resolution.
Right. So we can take the, a 2-degree Whorf model orography or something, put it over here.
Yeah, if you look at the cross section of land, it just goes up very quickly. Quite high. So it's, I don't know what geographic water feature is, but it's something.
So any onshore winds have to split
Right.
near the surface.
Can we not, I don't know whether, can we not just, in our forcing, we introduce artificial stress? Would that also?
That's what the guy who did Monday more.
That's basically what he did, right?
But
He artificially moved that to one group on inwards.
Won't your, model, it should try to get it back to what's supposed to be in the equilibrium? Like if you run it long enough, shouldn't it? Because what you're saying, some kind of an energy balance.
there's no energy balance. It's a
The
force.
ocean mode is
It's a
forced
force.
by the sea side, and in
No,
case
it's
of
not.
it, there's no way the ocean mode can bounce back.
Oh, okay.
If you're talking about a couple system or something, then.
Couple system doesn't balance.
Here,
These are momentum. Again, momentum is not balanced when you have a force. Friction.
Okay?
Okay. The whole point here is that changing the Core 2 forcing to Whorf simulation forcing. The main difference is that along the coast, the warm SST bias is largely reduced, and we got a cold bias here instead. And just to notice that in the open ocean, like here and here, the wall forcing actually gives a slightly larger warm SST bias than the core 2 forcing here. Okay, so how about the subsurface features? And just notice here I did some blue lines here. So this one is at 23 degrees south, and it's at the core of this warm bias. And these two lines are, this one is 18 degrees south, and this one is 26 degrees south. These I made these two lines at the the two cores of this cold bias features here, and I did a cross section compare of these three lines here.
You should probably put this line in the same place in both 23, 22. So it makes it easier to compare.
Okay. So here, this one is core 2 forcing at 18 degrees south, and this one is wall forcing at same degrees. And this one is the difference between the wall forcing and core 2 forcing.
You do have it in the same place. Okay. So,
It's only the labeling point.
Okay, and these two panels are for 23 degrees south and 26 degrees south separately. And we can pretty clearly see that for the wall forcing at the coast, there's a very strong upwelling feature here. But in the core 2 forcing, there's just a very narrow band of like upwelling here. And for these 2 degrees, also they are like the same. Along the coast, the upwelling feature is pretty strong, and for the core 2 forcing, the upwelling is pretty weak. Here I plot the differences between these two, and the results shows that it's very interesting that along the coast, the wall forcing temperature are much colder than the core 2 forcing, but for almost every other place, the wall forcing is actually warmer than core 2 forcing here.
Can you explain why?
That I'm not very sure.
Okay, so that's something you need to work on, right?
Yeah.
You don't want to just tell people this is the difference and
Yeah, I know. Just
don't have an explanation. Whenever you see something, you always ask yourself, well, how am I going to explain this? Right?
Yeah.
I'm a little confused. We're looking at differences
the bias is both
in temperature.
yeah, temperature.
And what do we, so you just superposed on the difference field the isotherms from some one of the fields? I don't know.
What are the contours?
What are the contours?
The contours are the temperature.
Okay, I'm also confused though. So is it 20
Temperature or
degrees?
temperature difference?
No,
This
it's
is
not.
the actual
No,
temperature.
this
Here is the
actual.
difference.
This is
Oh,
actual
so it's
temperatures. These two, and this
Yeah,
one
this
is
is the
the
difference.
difference between Wolf and core 2.
So that's why this scale
This,
goes.
this minus sign just means
It's the
this.
dash height.
It's another type.
It's not minus.
Yeah. So this is actually the actual temperature field,
All right.
and this is the difference.
So the thermocline is in a different place, and that shows up
Yes.
strongly and has 23 degrees
Yeah.
south.
Right.
What deepens the thermocline but gets the upwelling?
Looks like that way. I mean, they probably have kind of a overturning cell goes like this.
Yeah, if you
Actually, it's slightly different. Like what happens in core forcing is like the spatial gradient of core winds is slightly away from the coast.
Yeah.
So in core forcing, you'll have the upwelling slightly away from the coast.
Yeah.
That's why you see a warm bias, slightly away from the coastline there. That is actually caused by the difference in wind field.
But the thing, you'll always get some difference in SST because core forcing has an implicit SST data set underlying it, I'm sure. Which may not be the same as what we used to force. What SST did you use to force WRF?
Reynolds.
Wharf.
Reynolds.
But whenever they did core forcing, they probably used an SST data set to do that.
For the winds, what they did is they took the ends of winds.
No, I'm thinking about SST. They probably use some. So there's always an underlying SST assumption there.
For which
Core. I mean, they got the surface air temperature, right, from somewhere.
Yeah.
Did we announce it or something?
Yes.
And so for that reanalysis, use some SST.
That's true.
Okay.
So there is underlying SST in the core data set. It's not in the data
It's
set.
a Reynolds.
It's also Reynolds? Yeah, so then it's.
Except that I think when
I don't
when Chris was the work model, the resolution SST is much higher. So she actually used the satellite-based blending. I mean, they all kind of call it Reynolds because Reynolds is.
Yeah, they're different.
Yes, that's one of the reasons we are confused. I mean,
But they
even in
all
preparation.
But I was worried that
blended
if
temperature.
you take any two SST data sets, there's some small differences.
Right.
Sure. Could be.
Right. That could be reflected. That's the reason why away from the coast, you actually see some differences.
But I think it's more to do with the winds because if you look at the wind profiles, it's very different. The structure of the winds, wind profiles are very different near the coast.
But away from the
Actually,
coast,
if you just overlay the difference, the wind profiles along the same latitude, you can see a correspondence between the difference in wind profiles and the spikes of blue and red colors in the different.
But do you think the fact that the warming is so broad, do you think that can be explained?
what about the
That
warming
seems
away
to
from the
be, that
coast?
seems to be too broad to really.
Yeah.
Just has energy.
One possibility.
Discussion of using core forcing but wharf winds or something like that, right? Wasn't there a topic?
Yeah.
Yeah.
Okay.
Yeah.
So all the radiations.
Already. Actually, cause of the wind. That's what.
Okay, so it's all because of the wind.
Yeah.
So you get even the big bias though.
Right.
The warming because of the wind.
So it's like this. This is the longitudes, and if you make it longitude, forcing how it case the peak is close to the coast, and there is a sudden drop of here.
Okay.
So in this case, you get a very high curve near the coast, so you'll have more upwelling near the coast.
Right.
So here there is more curve in this region, so there is an upwelling here. So when you make a difference plot, the core is cooler offshore region and warmer near the coast. That's basically those
So you get
patterns will be
dipole.
corresponding to each other.
And if you look at the velocity field of core 2 force, I think it's pretty consistent with that. For I'll show later. And
No, but I'm more concerned previously. We go to the previous page, not this one this one.
this one.
The general warming everywhere, right? That's.
Here.
Yeah.
Yeah.
And that could be
It's
due
the
to the
same.
SST. That could be due to the SST.
That's actually not that different between the two. Okay.
It's a bias.
Go ahead. Next one.
For the next one,
Pineapple.
okay,
Really?
this is the meridional velocity.
You're using like a fraction of your color range.
That's why we should ban using the color from now on.
Yeah. Okay, now this is the at these two latitudes. So here are the 8 degrees south, and here are the 23 degrees south. I didn't compare the 26 degrees south here. And for the 18 degrees south, this one is the core 2 actual V, and this is wharf forcing actual V. And this is the difference between the core 2 forcing and velocity, and this one is wall forcing, comparing with the CFSR velocity here, and the CFSR velocity here.
Yeah, question.
Well, actually, I forgot.
The
It's
thing is,
also like 1
Do
degree.
you want to treat for these small features? Do you want to treat CFSR as true?
Well, actually,
Probably not.
probably not yet.
Okay.
It's
there's
just
nothing-
nothing else we can compare with. Yeah.
There's no truth, essentially. That's the problem.
Because it's going to have similar problems trying to get that right.
CFSR is half big.
But at least we start our models from CFSR, so it has some. We can do some comparison between the model results and CFSR.
Because at least in SST, you have satellite data, you have some truth in it.
Yeah.
Strongly influenced by models.
Okay. So generally, the wall forcing have a better simulation if we consider the CFSR as true. Have a wall forcing have a better simulation than core 2 in case of this Mariana velocity. But here at 18 degrees south, I noticed that here there is a countercurrent from north here at 8 degrees.
It's very confusing. You've got 18, and for the big 18 picture here, but you had them all at the same.
I think the all panel up there is 18, right?
Yeah, all panels up there are 18.
18.
Size.
Those
This
are
is
different.
just our
And so then the top two looks like that's the core 2 forced ROM simulation.
Yeah,
and
this
then
is
the bottom two panel is wall forced.
this one is core 2 only, and this one is core 2 minus CFSR.
Oh, the bottom.
This is the bias here. And we see in the CFSR field here, there's a countercurrent that's probably a but we see in the wall forcing, this countercurrent actually moves westward to around 8 degrees.
Westward. You mean
Yeah.
this is the V velocity?
V.
You mean north?
No, I mean this feature.
Oh, the
Alright,
feature.
Yeah, the feature moves westward. Okay, so I haven't looked into details of this, but I think I may do something maybe in the future.
Does it mean away from the coast?
Away from the coast. Yeah, so this countercurrent,
Why do we call it a countercurrent?
because here is the Benguela current from
Where
from
are you? You're at 18 south.
south.
Where's the Benguela current?
Benguela current is
I don't think the Benguela current goes to 18 south anymore.
well actually
That's actually frontal.
the frontal zone is slightly north, and this is approximately at 16 degrees south. So well, what I mean is that for we actually don't see any northward flow in the core 2 forcing, but for the wall forcing we see very strong northward flow, which means that
Well, it's very
It's
strong,
not very strong.
so it's here.
very strong in a very shallow region.
Right.
Yes, pretty shallow.
So the transport is not.
It's not very strong. So which one do you think is more reasonable? Is the
Well,
warp-
actually,
is the
I
warp
think-
thing- is the-
Actually, I think the position of this southward flow, core 2 force makes more sense, actually,
Why?
because here if we look at the CFSR,
Are you trusting CFSR?
not completely, but
Where is the frontal location located?
The frontal is 16 degrees south.
Okay, if it is, let's assume in the front stays in the 16 south, right?
Yeah.
So north of the front, the current should be going north and south.
The north of the front should be going southward.
Okay, and the south of the front should be going
Northward.
So 18 south, you would expect the flow going north and south.
North.
Okay, is this going north?
This one is going north.
Gaia.
That is the problem.
Tiny feature. Glad I brought my glasses.
Is this really a value or is it just?
Well, the problem is
I
that
think the only reasonable
we don't have
analysis
this.
we can do is the lower left floor on the left-hand side and the extreme right panel bottom side. Because the 80 degrees south is too close to the frontal zone. Any difference between the frontal location model and CFSR will get you a very different.
I think 18 degrees south, you should expect the flow move more northward than southward. I think
Yeah, you should
CFSR is
be.
actually wrong.
So 23 is a safe place, and if you compare the WARF simulation with the CFSR, it's probably similar. You have a northward flow very close to the coast, and
That's
you have
right.
a southward
I mean, the
flow.
fact that the core are actually giving the southward flow, it's because the Angola currents overshoot. You have too much. That's the
Yeah.
reason why we have the warming.
Yeah.
We have the southward flow from the north actually going too strong.
what I mean
Wind
is
cross.
that the Angola current, if Angola current overshoot is going to the subsurface feature,
No.
right?
So that means your
That's not true.
CFSR is doing bad, or CFSR is also not showing it the way it should be.
See, one of the problems.
In reality, in the real case, the Angola current should be going subsurface.
Mm-hmm.
But in this case, because the front is moving way to south.
Yeah.
So the current is actually pushing all the way to the south. That's the reason why you can see in your picture here, you can see the southward flow all the way penetrating through to 23 south.
Mhm.
Okay, you don't want to compare the CFSR too much.
I don't think you should be comparing with CFSR at all.
So one of the problems is we don't have any observations or any other data set for this kind of comparison.
Right.
Yeah.
So
You see, and
either you
this
have to
is
go
much
for
more
some
reasonable.
sort of reanalysis and
This one, yeah.
This is the upwelling induced the
Yeah.
Angola current.
Yeah, and this is-
Underneath this
This
is
Angola
where the
overshoot.
Angola current. That's the
you see
undercurrent.
the same feature in CFSR too, the bottom part, right side.
The 23 is probably correct.
Yeah, that's the only fair comparison we can make,
Right.
I guess.
But 18 is definitely not
Do
right.
they have measurements of surface flow?
They do. Well, the problem is that we can get the data, right? That's the
Oh,
problem.
okay.
We can't get the data.
But there's some Chinese connection you could get. That go in there.
Well, that's the thing, yeah.
It's very complicated.
It's all
We
very
don't know
complicated.
for years, individual years, but we have a pretty good climatology from surface days. The climatological field, we
So I would recommend that when you go back, feeling to see what is the general circulation in this area look like, since you're going to do a PhD dissertation on this, right? So in a couple of years, you're going to be an expert in this field, right? So you need to know all the literature, and you need to know that, what is the observation, even though we don't have really much observation. Read all the descriptive, there are some observational work over there. So you should get a feeling to see what kind of general circulation feature this region really look like.
Mm-hmm.
And you can't just naively taking a ring and ask those to choose.
And don't focus on features like that one for your
Oh, yeah.
arguments. That's so small. The one on the top right corner.
Always trust something really observation,
I think that's
in situ
obvious.
observation.
I know,
Not
but just
trusting things that's modeling involves.
I had a quick question, why do we see, in the depth, why do we see features in the longitude direction, some kind of,
Which figure are you talking about?
on the left, take any figure, all four of them, any of them.
Uh-huh.
We see a meridional structure, not meridional, sorry, zonal structure.
zonal structure, I mean, probably
Alternate.
already 20
in the not
below the surface. Well, actually, I'm not pretty sure about this.
Say that again. I didn't quite
It's
get.
alternating.
You see, maybe like 20 meters below the surface, there's always like a boundary here.
no below that.
Below that?
Yeah.
You,
What depth, what depth?
so you see,
What depth?
you see alternating features? Is that what you're trying to say? Alternating
It's not
features.
alternating, but like it's like
You could see bands clearly.
Bands,
That's
yeah.
bands.
We don't see that in CFS.
No, well, I mean, you have to believe, I mean, you have to remember there are lots of mesoscale eddies.
exactly, yeah.
Yeah.
So near the
We
coast,
saw it during the previous temperature. Previous.
near
There
the
are lots
coast,
of
there
mesoscale features.
is
here.
a currents flowing north and currents flowing south. Away from the coast, you have mesoscale features generated from near the coast. These will keep moving westward. So at any given location, if there's a cyclone, you have, like a deeper, like central temperature. In cyclones, then you have, like shorter central temperatures.
Okay.
So then you see this kind of oscillating features, that these can have signature deeper than 40 or 400 or 500 meters.
But that's like a 5-degree eddy. CFS should get that. Right?
And
5 degree.
not just that, it's an annual average.
This is an average. It's probably not an eddy. It's
Yeah.
just a kind of like remnants of whatever
Yeah,
eddy
the
at the
problem,
end,
yeah.
exactly.
But that's not.
So what you want to do is actually, if you look at animation, the temperature or sea level height or whatever, you actually start to see this mesoscale feature. And when you take the time average like that, you basically look at something as being average. You don't know what the thing really is.
So anyway, these are some kind of conclusions for the figures before. And let's just take another look at the surface velocity field of these two. On the left is right. We can clearly see that. So first of all, the coastal current. We see that in core 2 forcing, the coastal current is relatively weaker than the wall forcing here. And well, let's see the frontal zone position here. So in the core 2 forcing, the Angola current moves northward and the Angola current moves southward, and they meet at approximately 18 degrees south, and they flow westward here. So in the core 2 forcing, the frontal zone position is around 18 degrees here. But in the wall forcing, we see that the Benguela current go all the way to 16 degrees south, and it meet with the Angola current and flows westward. So the frontal zone position actually, in the wall forcing, the position is actually to the north of the core 2 forcing here.
I would say we should show this picture before all of the picture. This is very clear and
Yeah.
show what's going on.
Yeah.
Much easier to interpret like a previous figure if you know this. You've been talking about it, now you actually see it.
It would also be nice if you could show wind stress.
Yeah, just
And that could help
Yeah.
interpret this.
having
You can also make I would like to see animation of this actually.
all animations.
And
Yeah,
just,
yeah.
every snapshot, we can actually look the variability simulated by these two sets.
Yeah.
You already have all those data here. You might as well take advantage of this.
So do you have a similar picture for CFSR?
No, I
Might be
didn't.
good to put that
Right.
up. Also.
You can do the CFSR as well.
I have a feeling it's going to be different.
I think it's very different.
Do you think the land location is very different from core 2 to core 3 during that period?
What location?
The land location.
Land location? Why would-
Yeah, because.
Why would that location change?
The land location is actually
Oh, you
related
mean
to the
because of
versus-
resolution? Because of resolution.
Yeah,
The resolution. Yeah, you mean the landscape boundary, whether the
Right.
landscape boundary is the same. Yeah. coastline.
Well, yeah, you could plot the coastline in the native grid of the.
I think,
data.
yeah, Chris did that, yeah.
The problem with contour forcing is there is no land boundary for that. I mean,
Oh,
there's no
it
land.
is like stuff
See,
like that.
I
Oh,
went into all these details of land sea masking area. For Porto, there is no official land masking.
Landmass, yeah,
Actually, yeah, because each ocean model have different landmass.
that's right. They don't want to do that, actually.
But that's the problem. They said that you need a landmass. That's what it said. You said just tell me that.
No, it's not that simple.
No, but a forcing data set with no landmass will never give you the boundary stuff.
Yeah.
Will never give it to you. So there's a fundamental philosophical issue there. Ocean models.
In that perspective, Portal is really bad because the input data comes from different sources and they have different spatial resolution. And none of them have land sea masking.
Okay,
Okay, and just one more thing to mention is that in the open ocean, the flow in the core forcing is actually pretty strong here, but in the wall forcing, in the open ocean, the flow is relatively weak here, which I think is pretty consistent with the what Jason just said, that the core forcing, the wind forcing is a few degrees away from the coast.
It's almost like the landmass is 3 degrees away. That's a huge difference.
so
Yeah.
do you think those are actually the Ackermann flow, or this is actually the geostrophic flow? I mean, if those are the Ackermann flow, I would agree that Jason is probably correct, right?
Yeah.
Yeah.
But if it is a geostrophic flow, then that's a different story.
Well, if Ekman for that with some kind of vertical component to the plane.
Right.
Well, at least I think along the coast here is pretty much the Ekman.
Then I guess plotting the wind stress would help.
Yeah.
To prove to how 4-panel plot these two and the two wind stresses.
Or you can compute Ackermann flow directly from the wind stress, right?
Yeah.
So then you will know, you can take the difference between, this is the model outputs, right? So you can decompose into Ackermann component and the geostrophic
Yeah,
component.
just separate this.
And then you can separate the two, then look whether,
Yeah,
how different
Ekman
they are.
or
right? So before you join the conclusions, you should do some analysis like that.
And this all, you can also see the bounded structure here. Because it is, right? If you look at V, you see the boundary.
So if you see lots of eddies, I doubt it's actually the stress.
Yeah.
It is due to the beach space.
The stress is not going to directly give you eddies.
Yeah.
On the surface of beneath that. So maybe there are eddies already on that region. It's already, on top of that, push that.
Okay. There's one huge problem that we have been facing with is that we lack the observation data for our study, and now we actually have some observational data, and I will do a brief introduction to that. So the database is from Tianjin International Ocean Information Center in China, and well, sorry for the Chinese figures, the Chinese characters. This figure is what they sent to me, just showing the distribution of the temperature and salinity observational sites in our study region. And when we see that, we got pretty excited here because there are many observational sites along the coast, which we think we can make good use of. But
What kind of sites are these?
I think they are, well, actually for the temperature and salinity, I think they are CTD. Just as a-
speeds. So mainly, like you can see those lines there, right?
These lines are
lines, and
from
XPDs are
ships.
used in ships of opportunity. That's what they call.
Oh,
They
so
give XPDs to the ship people and they deploy them in available places and they have an XPD.
okay, so this is like a common-
Temperature, just temperature and the depth.
Yeah.
There may be other pieces, but we don't know much about those sources, right?
Okay, but we got a lot of observations here, but actually these are the data that they have collected over decades. So how about in 2005? In 2005, there actually are not many observations. Yeah,
What are all
the
dots?
most close to the coast is few observations
What
here.
about all the dots in the previous picture? Very close to the coast?
No, these are in other years. Actually, this is a figure that they showed all their data. They
Well,
collect
but, you know,
the
for
data.
this purpose, we can just look at climatology.
Yeah, look at the.
You don't have to get it that particular year. We can get a first thing to do would be develop a climatological view of this region.
So nobody has done that?
I don't think so.
That'd be very useful for us.
Yeah, just don't worry about, don't look at the year, the data just in particular. Look at all the historical data. You draw a line along, you have a line along the coast, right? A degree or two along the coast. And then take a few sections. So let's look at the salinity and temperature profile and to see what they look like.
Yeah.
Right? So Jason has about 20 years simulation already for 9 kilometers.
Yeah.
So you can derive,
you
can construct climatology based on that run.
Yeah.
And then we can compare it to this climatological data.
Yeah. This is just because for
This could
for
be
my
a
reason.
study in itself, right?
Yeah.
Yeah.
You can analyze, I
Right.
guess you need to find
You
out.
can't just do regular.
Because you can't publish it without the permission of the people who provide it.
Right.
Yeah, I mean,
Actually,
You could have some co-authors and do it.
for investing too much time, that's part should be clear, like, we could use this data for scientific purposes.
So
Actually,
I would actually bring the data into a fine resolution grid, let's say, and then counting whatever the observation we have within that grid box, right? And average all the Januaries, and average all the Februaries, and average all the March and things like that. So you get a graded product along the coastline. So that would give us a feeling to see what is the three-dimensional temperature and salinity structure look like in this region.
Yeah, I always thought that the observations may not be very continuous. So I just did a.
We don't have to be continued. The climatology
Yeah.
is a climatology. So you take all the January points you have, right?
Yeah.
Do you think this data set is completely independent of the Whale-Ocean Atlas database?
I think so. I think the ones along the coastlines probably different. We can also, you know what? Actually, Ben Guys has the Ocean Atlas, but when he constructed the soda products.
Yeah.
What's the resolution of that?
Soda is about half
The
degree.
Whale-Ocean the Whale-Ocean Atlas, they have in different resolutions for different regions, so I don't know what they have for this region.
Often they tend to be coast, right?
Yeah.
So they may not get they may not be interested in the coastal thing, they may average stuff.
Right.
But this looks impressive, the coverage near the coast.
Yeah, this is probably how many years are there?
Are there some
It's over
blue points
decades.
on the land
Huh?
also?
It's over decades.
Okay,
I think
well,
it's,
that could,
like 20 or
get some information to see what the time span of this, and to see whether we can construct climatology out of this, especially along the coastal zones.
Yeah.
Okay, so that would be very useful thing for us,
You just trying to figure out what is going on.
especially if you have the three-dimensional structure.
Yeah, okay. But for my current study, I just take the observation in 2005, and it appears that the measurements most close to the coast are here, and there are only 4 measurements. So I just did a single point comparison between the observation and my models. So here, let me explain. Because the model output is average every 10 days. So we don't have a snapshot for one single day. So the first observation is in 2005, January 2nd. And the second observation is in 2005, January 12th. And we cannot just compare the observation with one single day of the model because we only have 10-day average output. So what I did is that I average the first two observations and compare it with the average of the first 10 days of the model. So it gives the first figure here. And for the other, for these two, I did similar things. Average these two observations and compare with the 10-day average of the model results. And for the last figure is average of the first month. Okay, so there is a big problem about this comparison is because the observation is in January. So it's only the start of the model. So maybe the model is has not been spin up. So I'm not pretty sure that you can give very good comparison to do that. But since these are the data that only have that close to the coast, so anyway, here we can see that for the surface, okay, the red line shows the wall forcing, and the blue line shows the core 2 forcing, and the green line is the observation. Okay, we see that in this region, at the surface, the wall forcing temperature is lower than the core 2 forcing, and well, the mix. If you notice the mix layer, the wall forcing. If you notice that here, the mix layer gradually got destroyed for wall forcing.
So the green line doesn't go to the surface?
No, the green line didn't go to the surface. The observations is the particular spot. Oh, actually, I didn't provide one figure. Is that the first for the first observation, it actually goes to the surface. But since I did an average, yeah, for the other three observations, it didn't go to the surface.
So the model is initialized on the spin-up line?
Mm-hmm. Yeah.
But these things, you probably never get it to every observation. If the model is spun up, it's going to have a bias. That's right. That's what we show.
Or could it be the same? Oh, the boundary condition has a problem.
Yeah.
Yeah, but this is an interior, right?
Yeah, this is 25 south, so yeah,
so
it is interior.
Probably the model is biased. The model is going to have a bias.
Right, but the flow is this way, right? So if the boundary bias could still influence interior.
Right. The model bias could be due to something coming
Right.
from top.
Yeah.
Never going to get.
Yeah.
It's probably never going to be better.
Yeah.
And you can see both the blue and the red line up very nicely.
Right.
It's just a model bias.
Right.
It's not the surface. It's subsurface. Again, the most interesting thing when you have the surface.
That's the in terms of SST, that's probably the most.
But then you don't have
important thing.
quite that. Observation which go all the way to the surface.
Right.
Because that's where the width does affect its biggest.
But it's also very noticeable is that both core 2 and wall forcing, the temperature is cooler than the observation below, like 50 meters here. And which means that for both models, the stratification is pretty strong, stronger than the observation shows here. And for both models, the subsurface features are pretty much the same. So which means that the wind forcing is mostly surface, like
So this is saying
30
that
meters.
the model thermocline may be too strong compared to observation.
Yeah.
Because usually it's the other way around, right? Thermocline
Yeah.
Yeah, the models
But this is one of the
sometimes
cases.
too strong.
This is very strong upwelling rate.
Also, the upwelling is creating a too strong thermocline.
You shouldn't have much of the summer time, the very strong upwelling. So the model is probably underestimating upwelling strength.
Okay.
With the worst case, it's probably too close to the, when you're only getting strong upwelling near the coastline.
Yeah.
That could be.
If you have a good climatology of data which go all the way to the surface, Very useful.
Yeah, that might be good.
Yeah, I'm sure a lot of people will be interested.
Well, actually, in this figure, I just did a comparison in this spot, and I also choose some observation in this red box here, and I compare the same days as the previous ones. So this one is around 8 degrees east and 27 degrees south, and well, in the surface, models are doing pretty good. Their depth and thermal climate depth here is, yeah, they're pretty close to each other. But the problem is also the under like 50 meters. Here the models are all cooler than the observations. This is not
This is not
observation.
upward
This
But still has some.
yeah, this one is the red box at this region. So also in this region, models shows stronger stratification than observations.
Interesting, in the thermocline, they line up pretty well.
Yeah, that's
Yeah.
quite amazing.
And then the deep ocean.
Right.
Actually, we had issues with deep ocean in the very first round. So that's why we are in the boundary matching. And then it improved a lot. There could be
Yeah, I guess
still,
you're right, it's probably coming from boundary.
Yeah.
especially boundary crossing the equatorial region is very messy. Because, there can be accumulations near the equatorial region and it can propagate along the boundary and then get into the interior.
Yeah, I think if there's error, a lot of those errors probably coming from the Agulhas region, because this is where the currents actually affecting the boundary information into the domain.
Yeah, the ocean seems to be similar.
Yeah.
Okay, just for a short summary. So the first one, changing the model resolutions does not have a significant influence on the SST. And second one is that wall forcing can drive much more prominent coastal upwelling than core 2 forcing. So well, from my understanding, it's because of the coastal wind stress, but I'll read the paper and see the wind stress curl to do with that. And next one is that, well, for wall forcing, we see that in the coastal region, WRF is doing core 2 forcing, but in the open ocean and in the subsurface part, WRF forcing still is not doing very great. And well, yeah, comparing with observation, both models have strong stratification, and the observations here. And here are some future works that I'm planning to do. So first of all is to extend the comparison between observations and model results. So Jason's 9 kilometer run extend 9, and this was sites in 2009 here, and there are a lot more observations here.
We're not getting anything close to the code, so that's the most interesting. So
yeah, that's a problem.
Forget about the errors. Just do
Yeah.
That's
Okay,
the most interesting region.
Yeah.
You're not interested in
We're not interested in comparing year to year. Just getting all the data sets along the coastline. And let's derive a climatology first.
Yeah, okay.
And the other thing that I would suggest that for the resolution for the 9 and the 3 kilometers, don't just focus on SST. It's not very interesting. I mean, when you're comparing high and low resolution, because they're both being restored to the air temperature. Look at the other features. It's probably going to be interesting to do a repeated EFIB analysis for the 3 kilometer.
Yeah, sure.
And to see whether we can actually see any. I'm actually wondering whether the mesoscale eddy
Place in
Any, yeah, plays any role in balance the heat budget at all in this region.
You can definitely help them to do that.
Okay. And I might do some work about the availability index topic, but this is not the main point here. So maybe I'll do it when I have time. So the main purpose of this thing is that I found this upwelling here is has a very huge contribution to the SST bias problem. So what I think is that we can parameterize the upwelling strength. So we just not just look at the figures and look at the colors and say things, just to calculate it to like a number, and we can more easily do comparison things. And third, I might be involved in setting up our new couple models for this region.
I mean, for upwelling, if you have a model, the best thing to look is look the W, right?
Yeah, I know.
Have you actually looked at W?
For the model, we can look at the W, but if you want to compare it with like observations, we don't have W. So that's the problem. For
Right,
for the model only, we can.
Why you're so interested in comparing the upwelling strengths?
Because if you don't have strong upwelling, like in the core 2 cases, there's not enough like cold water from your deep ocean. So that might be one of the reasons that we get a warm bias here.
Anyway, how did the temperature and salinity work? What do you intend on doing?
Excuse me?
Based on temperature and salinity, you can't anyway get much of the vertical. Can you?
But in getting from PNS to get the other properties. You did assimilate it.
Yeah, you mean using the observations, the temperature and salinity? I haven't seen
Once
that.
you go to data assimilation, then Rob's how data assimilation more you are.
But other people have done it, right? But you want to do it again.
But I'm not convinced that this is a unique development, because all those lines you see here, this is definitely going to the railroad transverse data.
No, I'm pretty sure all the lines are, but the coastal one doesn't.
But yeah, we don't see any of them in any of these years.
Well, that's the thing we're trying to get. I mean,
So
you need to
I
follow
thought,
every year like that. Go back to see
I just
one.
have a documentation, they have this coverage maps for different decades, so we can clearly see any of these that's going there.
Yeah, then you can just, these are all incorporated in the World Ocean Atlas.
Then we don't have to worry about, computing the climate model, we could just use the railroad transverse.
Right, exactly.
Actually, they have a recent version in 2013 that includes the Argo ports and all new observations, so.
Right, but what's the spatial resolution of that in a sense? Normally it's very
For
close.
this region, I think it's 1 degree or 0.5.
Yeah, it's normally 1 degree by 1
Those
degree.
are
For
big.
Gulf of Mexico, they have a very high resolution, 25 kilometers, I guess.
But you need to look into this region, see how.
Yeah, I can ask for all the observations. Yeah, and like do the climatology along the coast. Okay.
Okay,
Thank you.
all right.
Anybody listening outside?
Anybody from the remote has any questions?
Chris is there.
Yeah, Chris, go back to back.
Yeah, just bring it up. Yeah.
Can you click on why the microphone is muted?
Especially
They
microphone,
prefer
that's fine.
themselves, I guess. It's not from outside.
Okay, ours is not muted.
No,
You can even type there.
Oh, that's a Q&A thing, that's not. Go to the
Oh,
chat.
that's not-
oh yeah, that's it.
Go to the left.
That's what I left.
Yeah, go to,
Oh.
click on the go up, one more next. Yeah,
This one?
click that, yeah.
That's the
Oh, that's
No,
the
this is-
one more side. So then go.
Yeah.
Oh, the top one. Yeah.
Ask.
Go.
Questions? She's probably gone. She probably couldn't hear you.
I don't think it's muted, but maybe the microphone's not.
Maybe she couldn't. Okay, anyway,
Yeah, that's one problem with the setup. There's no way of, testing it. If they bring the laptop, then there will be, like, feedback and
I know it works. Because
right.